Welcome to Module 3 on Louisiana's Precast Erection for Lake Pontchartrain Bridge Safety Base Substructure. We're pleased to welcome our speaker, Chris White, Senior Technical Advisor for Structures with Volkert, Inc., and Q&A panel members, G.J. Schexnayder, Group Manager of Heavy Construction with Bow Brothers Construction Company, LLC, and Hossein Ghara, Senior Bridge Design Manager with Volkert, Inc. Chris?
Okay. I am honored to be able to speak today about one of the United States historical bridges, specifically the Lake Pontchartrain Bridge in Louisiana. For those of you that are not familiar with where Lake Pontchartrain and New Orleans are located, New Orleans is down here on the very southeastern tip of Louisiana, where the Mississippi River dumps into the Gulf of Mexico. For many years, in the late 18th or 19th and 20th, early 20th centuries, Mandeville to the north was a kind of a getaway for the residents of New Orleans during the hot summer months. So they had longed to have a more direct route to get to their summer homes in that. And so that dream was finally realized in 1956 when the first causeway bridge was constructed. And let me tell you about that bridge. So the first causeway bridge was open to traffic in August 30th, 1956, and it became the longest bridge in the world at 23.86 miles. The bridge was completed in 19 months for the grand sum of $46 million. And no, that is not a misprint. The bridge, 5 months after notice to proceed, they drove the first piles on the project, and within another 14 months, they had constructed the entire 24 miles worth of bridge. And the reason they were able to do that is because they used an all precast solution, piles, caps, and precast superstructural modules. Now, a second parallel causeway bridge was built about a dozen years later. That bridge was designed by my company, which was known as David Volkert and Associates back then. It was built by the same joint venture that built the original bridge. The bridge is 228 feet longer than the first bridge, and it's still considered the longest continuous bridge over water in the world. Now, the fact that the bridge had to be 228 feet longer than the first bridge, I'm sure that was absolutely necessary, that no bragging rights were involved. But I could be incorrect on that. Now, several enhancements were made between the first and second bridges. So the second bridge, the spans were roughly 1.5 times those of the first bridge. And so the pile bench required 3 piles instead of 2. You can see the northbound or the second bridge on the right-hand side here, and the 2 column bench on the southbound structure. The girders were deeper, obviously, for the longer spans. And also the northbound, the new structure had a 31-inch high barrier instead of a 25-inch high. And finally, the original structure had 4-inch wall thickness on the cylinder piles, where that was increased to 5 inches on the second bridge. The bridges are 84 feet apart, and there are 7 crossover spans between them. Now, over the years, structurally, the bridges have performed very well. The main problems have been with the thin-walled cylinder piles. There has been some deterioration of the piles at the splash zone, and so quite a few of them have been wrapped with fiberglass. There's also been a few incidences where the simple spans, all of these are simple spans, have been knocked around a little bit during storm surges and hurricanes. And so there's occasionally a few, they have to come back and adjust some of the span lengths. However, the biggest issue has dealt with the increased traffic volumes over the years. Whereas the, originally there were 200,000 vehicles per year on the original structure. Nowadays that's increased 60-fold to 12 million per year, or roughly 40,000 vehicles a day, as you can see in this picture. Some of the problems that's caused, combined with the fact that the bridge has no shoulders, it's 24 miles long and it's got extremely low traffic rails, there have been some safety issues with the project, as you'll see in this video. Looking down here at this vehicle, unfortunately that truck got a little bit impatient and had to pay a high price for their impatience. So with that in mind, the owner, the Greater New Orleans Expressway Commission, hold a second. Okay. Undertook 2 projects to increase safety on the bridge. The first of those projects was to increase all the barriers on both structures. So that was 96 miles worth of barriers with the 36-inch high single slope traffic rail, which you see in this picture. However, I'm not going to talk about that project today. The project I'm going to talk about is the $60 million safety bay upgrade. That particular project involved the construction of 6 pullover bays on each structure. Each pullover bay is 1,008 feet long, and they were spaced roughly 4 miles apart on the structure. Volkert was selected to design the bridge based on a design competition. And the bridge was built using a CMAR contract, or what some states know as CMGC. So CMAR is Construction Manager at Risk. CMGC is Construction Manager General Contractor. This type of construction method is a bit of a hybrid between design bid build and design build. It allows the contractor and designer to work together during construction. And so from about the 30% phase on, the designer is able to tailor the design to the contractor's means and methods. So in that manner, it's like design build. Now, one big difference is in the contracting. With design build, the constructor and the designer are contractually obligated to each other. With a CMAR, both entities are separately contracted with the owner themselves. So now, once we were selected for the project, we were asked by the owner to prepare just kind of a short video showing the erection scheme we had proposed for the structure. We had proposed a scheme using all precast elements, piles, caps, superstructure. We figured it'd worked twice before. Why shouldn't it work a third time? And so this is a very crude, rudimentary video prepared in about a day and a half. It shows the general concept we had used in the design process. So again, the important thing was to keep traffic moving on this project, to minimize disruptions to traffic and to protect and provide safety for both the traveling public and the contractor and the contractor's workers. Now, these piles are not to scale, so please do not try this at home. Nonetheless, once piles were in place, caps could be set on top of them, and then the precast deck units would be positioned on the substructure. Once that was done, the existing barriers could be cut off and final barriers put in order to complete the safety bay. And so with that, I'll talk about the safety bay erection, in particular the substructure erection. What you see here is one entire safety bay with all of the substructure in place. All the piles have been driven and all the caps have been set on top of them. And the contractor now is placing the deck units. Now, again, I'm going to focus only on the substructure construction. You'll have to pay extra to get the full program. So any type of accelerated bridge construction really requires close coordination between the designer and the contractor in an alternative delivery project. And with that, I'm going to point out some of the differences between our original design concept that we had envisioned and that which evolved once the contractor got on board. So the northbound and southbound structures were fairly similar, so the construction means and methods were the same. However, there were some differences in the member properties. We had envisioned the use of the new Louisiana precast girder shapes. These were the LG25 for the southbound structure. And with that, we would have a deck unit cast in place. And then that entire unit would be set into place and have a cast in place closure strip at the deck level. We had proposed the use of a separate cap that would remain permanently separate, maybe require some bracing during construction. And because we did have a separate cap, we had looked at the use of twin piles there using, it's actually 36-inch diameter cylinder piles. For the northbound structure, it was pretty similar. These were longer spans. They were the 84-foot spans, so we used a deeper LG34 girder. But also, again, we had precast caps that were separate, and then also pair of precast cylinder piles. Now, we did also propose the use of diaphragms at the ends of the spans and also at the third points, and this matched the existing bridge. We were not really that concerned about it from having the diaphragms from a performance standpoint, but we were concerned during construction with the lifting of the superstructure sections in placement, so we wanted the diaphragms to add some rigidity to it. Now, once the contractor, Bow Brothers, who was selected by the Greater New Orleans Expressway Commission to construct the bridge, once they came on board, they immediately looked to making some modifications that better fit their means and methods. For starters, the types of forms, all the new Louisiana girder shapes weren't readily available from all the precasters. And so Bow Brothers asked us to switch the girders on the southbound side to using typical type 3 girders, Astro girders, which we did. They also decided that they wanted to use the larger diameter, a single 54-inch diameter cylinder pile, which is what was used on the original structures. And then finally, the biggest change they made was they wanted to, rather than cast the deck, make a connection at the deck level, they wanted to make the connection at the cap level for the substructure. And so from a structural standpoint as a designer, that was not our first choice. We were a little concerned with a 2 girder system in that. However, we definitely understood the advantage from the contractor standpoint of making discrete connections to the existing structure every 56 feet at the vents on the southbound side and every 84 feet on the northbound side, rather than having to connect the superstructure for the entire 1,008 feet of the structure. Now, pretty similar on the northbound structure. The similar, the Astro girders were used. This time the Type 4 girders were used. We still had a 1-inch open joint at the deck level and a doweled closure joint between the existing and cast in place and precast substructure. Now, one of the things that the Bow brothers had wanted to do on this particular one, they asked us to extend the cap out a little farther and also to use a continuous bearing seat. Because the northbound structure required that the existing barriers be cut off with a vertical cut, their plan was to go ahead and erect the superstructure elements, set them farther to the outboard side of the cap. That would allow them a working platform and give them room to be able to cut off the existing barrier rail, and then they could jack this superstructure unit into place up against the existing superstructure with just a 1-inch joint. One final request that the contractor made was to eliminate the diaphragms in the structure. So obviously that would facilitate his fabrication. Now, we did agree to eliminate the intermediate diaphragms. However, we felt that with having a 2-girder unit and still needing to lift these superstructure elements and that, we did not feel comfortable eliminating the exterior diaphragm. So those were left in place. And so with that, I want to get into detail on the substructure erection for this project. Now, I never like to pass up the opportunity on a presentation to also provide a history lesson with the topic at hand. And so with that in mind, I have asked my good friend, Mr. Peabody, to help me kick off today's history lesson. So back in 1950, an engineer, Maxwell Upson, with the Raymond Pile Company in New Jersey, had developed a process by which cylinder pipe could be spun cast. So he had a spinning form where you would inject concrete in and it would create a hollow-walled cylinder shape. Now, Upson also had the idea that this particular process could be used for cylinder piles for use in the brackish waters and saltwater environments along the Louisiana coast for the oil and bridge industries. And so with that in mind was the birth of the spun cast cylinder pile, which even today is still known in some circles as a Raymond pile. Now, the way these piles were used on the original bridge, so for the original structure, the contractor had set up an on-site precasting yard just off of Lake Pontchartrain where he could fabricate the deck units on the western half of the precast yard. And then the cylinder piles were manufactured on the eastern half of the prefabrication yard. As you see in this picture, here are all the cylinder pile units standing vertically, and here they are once they've been post-tensioned together to their final length. Now, the piles on this project were spun cast using what Upson called the Synviro process. The beauty of this process was that it allowed, upon notice to proceed, the contractor to immediately start fabricating these segments. They could be fabricated with a number of forms and then stockpiled and then post-tensioned together for final use when they were ready to be barged out to the bridge site. And so for the original project, the piles, as I mentioned previously, on the first bridge, they had 4-inch cylinder walls on the project. And the segment lengths were roughly 16 feet long. What that allowed them to do was to take 5 16-foot long segments along with one odd 10-foot long segment, post-tension them all together, and then they would have a 90-foot long pile to ship to the bridge site for installation. Now for the safety bay project today, the process of fabricating the piles is still pretty similar to what was used in Maxwell Upson's day. What you can see here are some spinning wheels that send this cylindrical form spinning, and with that they dump the inject the concrete into the center of the to the form, and it spins up against the walls of the pile until you get a very densely compacted concrete that forms the shape of the cylinder pile. And then once all of these segments are fabricated, you can then post-tension them together, as you see here, into a final pile length that can be barged to the bridge site. Now, the advantage with regard to the spun cast cylinder piles, there is only currently one precaster that's capable of manufacturing these piles. Fortunately, that precaster is Gulf Coast Pre-Stressing, located in Pass Christian, Mississippi, which was relatively close to the project. There had previously been a precaster on the East Coast, Bayshore construction, that unfortunately, however, they shut down operations several years ago. There are other fabricators that can make what are known as static cast or bed cast cylinder piles. These are just cast in a horizontal bed to the final pile length, much the way a square pile or a octagonal pile are cast, except they use a retractable mandrel in the center of them. So why were spun cast cylinder piles chosen for the safety bay project? Well, first of all, the high axial load capacity makes them ideal for this particular project. They could be done with just a single pile at each bent. The cylindrical shape and the large diameter, 54 inches in this application. They have enhanced lateral capacity, particularly where you have deep water or where you have soft soils requiring greater depth to a point of fixity. However, one of the most important things, both for the original structure and for the safety bay project, had to do with really where the accelerated bridge portion of this comes into play on this project is not so much into the installation of the piles, but rather into the fabrication of the piles and getting them stockpiled. So as part of the CMAR contract, the owner had allowed for an advanced procurement contract for the piles. So Bow Brothers was allowed to order 80% of the planned quantities in advance of the final construction contract. So with that in mind, he could immediately get Gulf Coast Pre-Stress started in fabricating the pile segments, which could then be stockpiled, as you see in this picture here. So that greatly accelerated the production schedule. It also allowed Bow Brothers or Gulf Coast Pre-Stress to start fabricating these segments before the pile test had been performed, and before Bow knew exactly what pile lengths they would need at what locations. And so with that in mind, these were an ideal selection for this particular project. And now on to precast pile caps. And as with the original structure, the pile caps were precast and were set into place on top of the 54-inch diameter cylinder piles. However, the application and how these were fabricated and then how they were transported and erected varied between the original projects and the safety bay project. For the original causeway bridges, the contractor cast the pile caps in an inverted position with the pile plugs pointing upwards. You can see in this picture the cages for the pile plugs. There were 3 of them here, which indicates that this is for the second causeway bridge. So the contractor could then fabricate, he would cast these caps in the inverted position. And once they were cast, he would ship them, barge them to the bridge site. And they were barged in the inverted position as you see in this picture. And once they got them out to site, the contractor would use the rigging to flip them over to the appropriate position, and he could then set them into the, so that the cages would be inserted into the piles. Now this particular picture is from the original bridge, because you notice the 2 pile vents. One of the things that was unique about the original structures is that the caps themselves were only 3 foot 6 inch diameters wide. So they were actually narrower than the piles themselves. What this allowed was when they set the caps on top of the piles, there was actually access to the annular space of the cylinder piles. So the contractor could grout the pile cap to cylinder pile connection from outside the face of the cap here. Now for the safety bay project, Bow Brothers elected to fabricate the pile caps in their upright position, and in fact to fabricate them without having to extend the cage out from the cap during casting of the cap. So they used splice couplers at the bottom of the simple rectangular forms. And with that, once they cast the caps, they were able to screw the vertical steel into the bottom of the cap and fabricate the cage. These precast segments were then barged out to site in the upright position using a special mounting device on the barge. And that way, Bow didn't have to flip the caps before setting them into place in the piles. Now, another unique feature of the construction method that Bow used for this project is visible on the right-hand side here. Because, you know, as I mentioned previously, over the years, some of these spans had been knocked around a little bit. And there was no really survey that covered the elevation of all the existing spans and how they all lined up. And so with that in mind, Bow Brothers ended up shimming the pile caps using 2-inch diameter PVC pipe that could be cut to appropriate length at each location. Those were then filled with epoxy, and dry pack was used. And with that, they were able to actually set the each cap to the required elevation to match the existing bridge for that span. That was especially important because Bow had also elected to cast the bearing seats as part of the prefabrication process. So there wasn't a lot of room for adjustment once the caps were in place. Now, one change that they did ask, or one provision they did allow for additional adjustment, was they asked us to detail some steel shim plates with 1/4-inch increments so that those could be stacked on top of the bearing seats and underneath the bearing should they need to raise any of the bearings so that they could get the deck units to the appropriate level. As I mentioned, this was a collaborative process between the designer and the contractor in the final design phases. Earlier, I mentioned that originally the contractor had asked us to extend the caps out and use a continuous bearing seat. So his plan was actually to set these units into place on the outside of the cap, to go in and cut off the barrier here. And then once that was done, he would be able to jack these, jack against the girders and jack this unit into place up against the existing structure. Ultimately, Bow Brothers decided against that, and they opted to use self-propelled modular transporters, or SPMTs, to erect the superstructure elements directly off the bridges, or off the barges. A few other modifications they had asked of us was to decrease the width of the closure joint, and to use headed bars rather than a conventional lap splice. So we worked up a detail for that. Here you'll notice too how the new caps are significantly wider than the existing cap. A couple other things. In our original concept, we had envisioned our cap was, as I mentioned, wider than the piles themselves. And so we had envisioned the use of a large diameter cylindrical pipe, much as Mike Colmo had talked about in his first presentation this morning. And then once the cap was set on top of the piles, that would allow the contractor then to drop the cage into place and then to grout the entire assembly from up above. Now, as I mentioned, Bow Brothers opted to actually have the cage be part of the cap once they got the cap cast and the cage and the bars inserted into the cap and the cage fabricated. So with that in mind, they did ask us to reduce the diameter of the cage so that they would have greater tolerance for setting this cap and setting the cage into the pile. And that was discussed in both Mike's presentation and also the Washington State presentation about having tolerances in that for placement of precast elements. Bow Brothers also had a shorten or to use just an 8-inch diameter conduit here going through the cap, and they grouted through that. So once all of the piles had been driven for a safety bay and all the caps were in place, the contractor was able to use one single operation to grout both the cap-to-cap cast in place connections and then also the cap to pile connections that we just previously discussed. And then once substructure erection construction was complete, the contractor was able to go ahead and complete construction using SPMTs to place the prefabricated deck units. Once those were in position, he was able to cut off the deck, the existing barrier rails, and then do final adjustments on the deck units. And with that in mind, a very successful project was achieved. What you're seeing here are two of the completed safety bays, one on the northbound and one on the southbound side of the structures. And again, a view from up above of a completed safety bay, also showing the new 36-inch diameter or 36-inch high barrier rails. The project did meet all of the project objectives, the traveling public objectives, and the owner objectives. It provided safety to the traveling public and to the contractors' workers while minimizing disruption to traffic during erection. And the project was also finished within the owner's budget. From a acronym buzzword standpoint, we achieved quite a few acronyms, accelerated bridge construction, pre-stressed bridge elements and systems. We used construction management at risk, and we even were able to utilize SPMTs on BARGESs. So all in all, the project was a resounding success. Now, just as the original two bridges, the second bridge borrowed heavily from lessons learned on the first bridge and used similar means and methods to the first bridge, the Safety Bay project also borrowed from its predecessor projects in developing concepts and means and methods necessary to enhance safety on America's longest bridge. And with that in mind, I'm going to just close with a nice video that Bow Brothers had put together of the overall construction process. I do also want to, at this time, both on the behalf of Volkert and Bow Brothers, to thank the owner, the Greater New Orleans Expressway Commission, and Carlton Dufresneau for their allowances to allow the design build team to do the work, but at the same time to be present and to be willing to make decisions that needed to be made from the owner's perspective in a timely basis. With that in mind, here's the overall process. A couple things you'll notice. We have one pile being hoisted into place while second pile is waiting on the barge. We talked a little bit about some of the discussions on how do you get caps on top of piles and with the variability in driving. One thing you'll notice that Bow Brothers did very well, they at each of the bent locations, they drove spud piles and set up a frame and a pile driving template. So that's one of the best things you can do, is to do everything you can to get to make sure you're aligning the piles to achieve success in that manner. What you'll notice is while all this is going on, traffic just keeps on moving with minimal disruption. Probably the most disruption they'll have is the curiosity of seeing what's going on outside the right side of the vehicle. This is a very good view of the bridge.
Okay.
And then, although I'm not going to...
Great job. Yeah, this is really a nice video. How about if we, thank you for your presentation. Can we begin the Q&A session?
You may
since
start
we only
it
have
now.
a couple of minutes now, and we'll just let this run because this is really exciting.
That'll work.
Paul? Okay, thank you, Chris. Paul, would you like to start the Q&A?
Sure thing, Mary Lou. We have a few questions that came in during your presentation, and we're about ready to go to break, so I'll try and do it. I do want to say that all the questions we've been getting, we are going to try and get all those answered and posted when we post the results of everything. The first one I have here is a person said, what was the purpose of the cast in place cap splice between the old cap and the new cap?
Well, it was necessary to have the two structures connected, and you're either going to need to do that at the deck level, or you're going to need to do it at the cap level. From a construction standpoint, if it were done at the deck level, you'd be doing 1,008 feet of deck and having to drill and dial into it. Whereas at the cap level, he was able to confine that to just the cap locations.
Okay. Then was it more cost effective to use prefabricated circular piles rather than maybe drill shafts?
Well, for this particular project, yes. Anything you do in the lake like this, first of all, the convenience of having Gulf Coast pre-stress nearby influenced the use of precast piles. But also drilling shafts in this type of environment, you would need to case the shafts up above and cast a column in the water. So it definitely made more sense to use driven piles.
Okay. Have underwater inspections shown any signs of deterioration at the joints between the precast pile elements, the old piles?
My understanding is the underwater elevations, they have shown quite a bit of deterioration around the splash zone. And that's really joints or no joints. Once you get down below the splash zone and get below the mud line, it's not a real deep lake. It becomes a little less critical because there's less oxygen down there. But there has definitely been a lot of piles wrapped, particularly with the old 4-inch walls and the 5-inch walls. New Bridge has 6-inch walls.
Okay, one more final question, then we'll go to break. How can we adjust the final top elevations? Is that done at the pile level, the bent level, or at the deck level?
Well, it's done at all three. First of all, it was done at the pile level by driving them to the correct elevation as much as possible without having to cut them off. Secondly, the use of the shim process, the cut to size shims that Bow Brothers did using the PVC pipe was able to set the caps to the right elevation. And then for any caps that were a little low, we could use those steel shims to raise the bearings up a little bit. So so.
Okay, that's all the time we have. I'm going to turn it back over to Mary Lou, and we'll go from there. Mary Lou?
Okay, thank you very much, Paul. We're at the end of the third 40-minute module. Thanks again to Chris for presenting the third module.